Now that we've introduced limits, it's time to put them to work and see how they provide a firm foundation for everything we've learned in this course. And where better to start than showing what derivatives really are? Think about the so-called black boxes in your life. Things that you know how to use, but maybe you don't really know how or why they work under the hood, so to speak. Things like maybe your car, or your computer, or even your toaster. All of these things are useful, and you can get through your day-to-day life with just a surface level understanding of them. But what if one of those black boxes breaks? Or what if you want to use one of them in an unusual or innovative situation? Maybe you want to trick out your car, or overclock your gaming rig, or make a new culinary creation the likes of which the world has never seen, with a toaster. If all you have is a surface level understanding, then you're greatly limited in your flexibility. Likewise, for many people, mathematics can feel like a bunch of black boxes. Nothing but a collection of procedures and formulas, each of which only applies to a specific situation. Like, think of the quadratic formula. You've probably recited it at least 100 times. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Possibly to some tune which I refuse to sing here. And you probably got the right answer to a lot of quadratic equations that way. But for one reason or another, many people never learned the rather beautiful geometric argument underlying the quadratic formula, which involves imagining the pieces of the equation as a rectangle, rearranging those pieces, and finding that last little bit to complete the square, literally, and figure out the unknown side length. It's an argument that not only explains where every part of the quadratic formula comes from, but can actually be generalized to solve cubic equations by completing the cube. That's the power of actually understanding how things work. So what we're going to do now is take a peek into the black box of the derivative and see how it's really defined. Recall that the intuitive idea we wanted to express with the derivative was the slope of a curve, to describe the rate at which that function is increasing or decreasing. So how do we find the slope? Well, we pick 2 points and find the ratio between the change in output and the change in input. You likely learned this as rise over run. The result we get is the slope of the line connecting those 2 points, a so-called secant line. But what we really want isn't the slope between 2 points on the curve, but rather the slope at 1 point on the curve. That is, the slope of the tangent line, barely touching the curve at that 1 point. How are we going to do that? Maybe we could just use the same point twice in the slope formula? No go. If we do that, then both the rise and the run are 0. So if we try to find their ratio, we get 0 divided by 0. That's a problem, as we've already seen. Now, what we did in our first lesson on the derivative was to reason that if we could somehow make the 2 points infinitely close together, whatever that means, with an infinitesimal change between them, then that would be infinitely close to the slope at 1 point. We'd have our derivative when we take the ratio between those 2 infinitesimal changes. And that's exactly how early mathematicians thought of the derivative. But that reliance on infinitesimals gave a lot of people the heebie-jeebies. I mean, just how close is infinitely close anyway? What does that even mean? And nobody really had a good answer. So the derivative was a black box. It worked very well, but it was still a black box. So mathematicians eventually did away with infinitesimals and rephrased that derivative as a limit. They thought, maybe instead of letting our 2 points be infinitely close together, we could just imagine that 1 point approaches the other to figure out what limit that ratio approaches. We could get within a millionth, a billionth, a trillionth of that slope of the tangent line, all by picking points close enough to where we want that tangent line's slope. So that's how we can define the derivative for real. If we have a function f of x and we want the slope of the tangent line when x equals a, We construct the ratio between the change in output and the change in input, and we find the limit of that ratio as x approaches a. And since x approaches a, x never equals a. So this limit keeps us safe from dealing with 0 divided by 0. As long as that limit exists, we have the slope at that one point of the curve. There's another way we can use limits to find the derivative, but this time it involves a little bit of clever relabeling, and it helps us think of the derivative as a function unto itself. What we'll do is we'll let our stationary point be x, and our moving point will be x plus a little bit, which we'll just call delta x, a change in x. We can calculate the slope between our 2 points just like before, but interestingly, if we do this, those two x's in the denominator cancel out to 0, and we're just left with delta x on the bottom. Then, to bring those 2 points close together, we take the limit as delta x shrinks down to 0. Remember though that since we're operating in the safety of a limit, delta x never is 0. So once again, we're safe from 0 divided by 0. What we're left with is a new function of x, and that's our derivative f prime of the original function f, finding the slope at any point of the curve. Let's test out our new definition on an old friend. The function f of x equals x squared. Suppose we want to know the slope of the curve at, say, x equals 3. Well, 3 squared equals 9, so we know that the graph goes through the point 3, 9. That's our stationary point. The other point will be free to move, so its coordinates are x, x squared. If we find the slope between these 2 points, we'll have x squared minus 9 divided by x minus 3. Now, we need to make those 2 points get closer and closer together, so we'll take the limit as x approaches 3. Can you see how we would do this limit? Well, taking a page from the last lesson, we can factor the numerator into x minus 3 times x plus 3, and then cancel out those factors of x minus 3 on top and on bottom. As long as we do so in the safety of a limit, we can guarantee that we're not attempting to cancel 0 divided by 0. So now we just have x plus 3, a linear function. That's continuous everywhere. So to find the limit as x approaches 3, we can just plug in x equals 3, giving us 6. So that tells us that if x equals 3, then x squared has a slope of 6 for that tangent line. Now, what if we wanted to find the slope at any point? There's 2 ways we could go about it. We could recognize that there was really nothing special about 3. We could have used any number a there. Then x squared minus a squared factors into x minus a times x plus a, and following the same argument gives the slope as 2a. Alternatively, to find the derivative function, we could let the stationary point be x and the moving point be x plus delta x, and then look at our second version of the slope formula. By taking the limit of that slope, we get the derivative. Let's do a little algebraic massage to that limit. If we multiply out x plus delta x all squared, we get x squared plus 2x times delta x plus delta x squared. So those x squareds cancel out to 0. Now notice that delta x can be factored out of the numerator, which lets us take delta x over delta x and cancel it out to 1. Now we've removed our danger of dividing by 0, so now we can let delta x be 0, and we're left with 2x. So the derivative of x squared is 2x. And notice that's exactly what we found long ago with the power rule. Cool, so how about, say, x cubed? Suppose we want the slope of x cubed when x equals some point a, so our limit would look like this. Now, remember how we factored x squared minus a squared as x minus a times x plus a? There's actually a neat pattern we can use to generalize that. X cubed minus a cubed can be factored as x minus a times x squared plus ax plus a squared. Try multiplying it out yourself. you'll see that all the middle terms will cancel out to 0, and you're just left with what's on the two ends. Notice how the powers of x go down while the powers of a go up. So in our limit, we can cancel out the x minus a's, and then use direct substitution to plug in x equals a. All three of the remaining terms come out to a squared. So if we add them up, we get 3a squared. Alternatively, if we want the derivative as a function, using that second limit form, we get x plus delta x cubed minus x cubed all over delta x. We can multiply that first power out using the binomial theorem. That's the thing that grabs the coefficients from Pascal's triangle. Or really, it should be Yang-Hui's triangle, but I digress. Anyway, we get x cubed plus 3x squared times delta x plus 3x times delta x squared plus delta x cubed. From here on, the process is pretty much the same as with x squared. Cancel out the x cubes, factor out a delta x from the numerator to cancel out with the denominator, and finally let delta x equal 0. And we find that the derivative of x cubed is 3x squared, just like the power rule says. Great. So what about x to the fourth, or x to the fifth? Once we've done x to the third, we can see how the pattern would generalize to x to the n. No matter whether you use the factoring argument or the binomial theorem argument, you end up with the same result, that the derivative of x to the n is n times x to the n minus 1. So that proves the power rule. Well, almost. Actually, it only proves the power rule when n is a positive whole number. It doesn't tell us what to do with negative powers or fractional powers. But those can be proven using things like the quotient rule and the chain rule, and each of those can be proven using the limit definition of the derivative. For general real powers, we would need to make use of the derivative of e to the x. That would mean we'd need to prove the derivative of e to the x as well. But we can also use the limit definition of the derivative for that, once we know that e itself is defined as a limit, one that originally comes from the idea of continuously compounded interest. So all of our derivative rules we've done can be proven either directly with limits or by using other derivative rules that can themselves be proven with limits. We don't really have time to go over every single one in detail, but the point is that you can, and that's how we know that they work. I'm wondering if you caught something I said earlier. When we were first looking at that limit for the derivative, I said, as long as that limit exists. But what if it doesn't? To see what I mean, let's look at a function we haven't explored much yet in calculus, the absolute value function. What is the derivative of absolute value of x anyway? Why have we never done that one? Well, first of all, it'll help us to remember how absolute value of x can be defined algebraically. If x is 0 or positive, then the absolute value of x is just x itself. While if x is negative, then the absolute value of x has to be positive. And that means it's just the opposite of x. Be careful not to interpret that negative sign as meaning the absolute value is negative. It really means switch the sign. And if x is negative, switching the sign makes it positive, just like we'd expect. Now, let's use our new limit definition to figure out the derivative of absolute value of x. Suppose we pick a stationary value a to the right of the vertex, that is where a is greater than 0. Now suppose x is close to a, and let's write out the limit definition of the derivative. Then the absolute value of x is just x, and absolute value of a is just a, because both are already positive. So the slope is x minus a over x minus a, which just comes out to 1. And that makes sense visually. The right half of the graph is a line with a slope of 1. If we choose a value of a to the left of the vertex, though, then the absolute value of a is the opposite of a. Since a is negative, its absolute value has to be positive, so we have to switch its sign. Same goes for if x is close to a, then absolute value of x is the opposite of x. So if we factor out that negative, we get -1 times x minus a over x minus a, which comes out to -1. And again, that makes sense visually. The left half of the graph is a line with a slope of -1. Okay, but what if our stationary point is at exactly 0? Now we've got a problem. If x is to the right of 0, then the slope is always going to be 1. So the right-hand limit of our slope is 1. But if x is to the left of 0, the slope will always be -1. So that's the left-hand limit. And that means the left-hand and right-hand limit don't match, which means that the limit that defines our derivative doesn't exist. We say that absolute value of x is not differentiable at x equals 0, because the derivative of absolute value of x is undefined there. It is differentiable everywhere else though. At any other point, the derivative comes out to 1 or -1. And it's even possible to write out a formula that encapsulates this. We can say that the derivative of absolute value of x, the slope of the tangent line at any point, is always equal to absolute value of x divided by x, as long as that tangent line exists. You can check that when x is a positive number, this comes out to 1, whereas when x is negative, it comes out to -1, and when x is 0, it's undefined, which shows that the function is not differentiable there. Notice that the graph of absolute value of x has a sharp corner at the point where it fails to be differentiable. A sharp corner is a telltale sign of a function not being differentiable, because the slope is changing very suddenly. There are other ways that a function could fail to be differentiable as well. Besides a sudden change in slope, you might have a place where the tangent line is vertical, so its slope is undefined. An example might be the cube root function. Or you might have a place where the function isn't even continuous, like, say, the floor function, also known as the greatest integer function. Not being continuous is an instant deal breaker when it comes to differentiability. A function has to be continuous in order to be differentiable. Though it's not a guarantee, as we saw with the absolute value function. That function's continuous, but it's not always differentiable. Put another way, differentiability implies continuity, but continuity doesn't necessarily imply differentiability. Math is full of statements like this. All squares are rectangles, but not all rectangles are squares. These one-way implications help you see the relationships between concepts and how they all fit together. We need to talk for just a moment about notation. I mentioned previously that a lot of textbooks and teachers will sternly admonish students not to think of dy over dx as a fraction. The whole thing is just a symbol for the derivative, they'll say. Dy and dx don't mean anything on their own, and you certainly can't split them up. Except that dx also shows up on its own when we're writing integrals. Oh, yeah, but that whole thing is also a symbol for the integral, they'll say. Then you point out that we solve differential equations using a technique that's literally called separation of variables. But people will still bend over backwards and do all sorts of contortions just to avoid the words infinity or infinitesimal. It just goes to show just how deep-seated the rejection of infinity and infinitesimals has become in calculus. Now, to be fair, the way we've now defined it, dy over dx doesn't really represent a single ratio of infinitesimal changes, but rather the limit approached by those ratios as the changes get smaller and smaller. That being said, it is actually possible to define differentials in isolation. If we define dy and dx as the changes we get as we move along the tangent line instead of the original curve, then dividing dy by dx does actually give you the derivative, since it's the slope of that tangent line. And if we solve for dy, we get f prime of x times dx, just like we saw originally and we've used multiple times. In this case, there's no need for dy or dx to be infinitesimal. When we use limits to define concepts like the derivative, and pretty soon the integral, we're able to sidestep issues involving the infinitely large and infinitely small. But while it's possible to sweep infinitesimals under the rug in calculus, that doesn't keep you from thinking in terms of infinitesimals to intuitively understand derivatives and integrals. That's what many mathematicians do, even if they won't admit as much in polite company. So, despite those admonishments, don't forget where these ideas originally came from. Like it or not, if it weren't for infinitesimals, calculus would have never even gotten started.